In this section, we're going to talk about the concept of work and energy. Let's first of all define work. Work is defined as the product of an applied force times the displacement. The work is done by the force itself. So in this particular case, this young lady, say, applies a force on the block, and as a result pushes it a distance of, say, 10 meters, then the amount of work done is 75 newtons times 10 meters, or 750 Newton meters. And a Newton meter is usually defined as a joule. So Newton meter is a joule. As a result of work being done by this force on this block, the block's motion is changed. In effect, the block gains kinetic energy. Whenever work is done by a force, a conservative force, one of the forces of nature, then the object gains energy in some way. In this case, it gains kinetic energy, and the amount of kinetic energy it gains is equal to 1/2 m times velocity squared. We can also do work against another force of nature. Say we lift a box a certain distance h. In which case we have done also work equal to the force times the displacement, and the amount of work is equal to mgh. So we say the block has gravitational potential energy equal to mg times h, which is the work done in lifting it from the floor to this height h. Another problem we considered in this section is the work done against a spring force, a restoring force. If you push, say, this block or pull the block from the spring, then we do work. And we push or pull the block a distance or displacement, the work is equal to force times that displacement. Since the force isn't constant, this is a little harder, but it turns out that the work done is equal to 1/2 kx squared, where k is the spring constant, the measure of how stiff the spring is, and x is the, in fact, displacement, the distance that we actually move the object. As a first example, let us look at us pulling a 100 Newton, 50 kilogram block with a force of 100 Newton at an angle of 37 degrees across a horizontal rough surface. In other words, it has friction over a distance of 5.6 meters. The coefficient of friction between the two surfaces is 0.1. So we're going to calculate the work done by all the forces that are involved. So first of all, let us draw a free body diagram showing all the applied forces. And this is what the free body diagram looks like. So the weight is down, the force of gravity, and then there is the normal force up, and if we have friction, it is going to be a frictional force to the right. So first of all, let us calculate how much work is done by the force F. To calculate that, why don't you stop the video and see if you can calculate it and show which one of these choices is the correct answer. So let us calculate it. In order to calculate the work done by a force that's at an angle to the displacement, we resolve the force into components. So in this case, the x component of this force is going to be 100 times cosine 37 degrees, and the y component is going to be 100 times the sine of 37 degrees. Now, it turns out that any force that's perpendicular to the displacement does no work. So we didn't have to worry about any work done by the y component, because this y component is perpendicular to the motion. The motion is this way. and the y component is up, the work done by it is 0. Similarly, the work done by the normal force is 0, and also the work done by gravity is 0. So the only forces we worried about is going to be the work done by the frictional force and the work done by the x component of the applied force. So let's calculate how much work is done by the applied force. Work is equal to force times displacement. Similarly, we're going to calculate how much work is done by the frictional force. Again, stop the video and see if you can calculate that. The work done by the force of friction, first of all, will be negative because it's opposite the direction of motion, equal to the force of friction times the displacement, which we know is 5.6 meters. Now the force of friction is equal to mu times the normal force. Now the normal force in this case is not equal to the weight, and that is because the sum of the forces in the y direction equals 0. That means there is no motion in the y direction. And the normal force plus 100 sine plus 100 sine of 37 degrees which is Fy, add up to 0, add up to mg. Forces up equals the forces down, or all the forces add up to 0. So the normal force is going to be a little less than the weight, and is going to equal to the weight minus y component of the applied force. In this case, that's going to be, the weight is approximately 500, we use 10 for g, and the y component, 100 sine theta, the sine of 37 degrees is 0.6, so 100 times that is equal to 60. So the normal force will equal 440 newtons. So the frictional force is equal to mu, which is 0.1, times 440, the normal force. We're going to put that in here for frictional force, put 5.6 for the displacement, and you should get the amount of work is equal to minus 245 joules. Now we'll begin looking at some examples of the law of conservation and energy, beginning with various energies that we've studied. And basically, conservation of energy states that energy cannot be created or destroyed, it's just transferred from one form to another, which means that energy at the beginning of any sequence will equal to energy at the end of any sequence. In the case of this energy lost to friction, then that amount of energy has to be added on. So the total energy is the potential plus the kinetic energy at the beginning equals the potential and the kinetic energy at the end. The types of energy we studied: gravitational potential energy, elastic energy, if we have a spring, and kinetic energy. These are the types of energies an object could have. So the sum of those three at the beginning has to equal the sum at the end. We're assuming now at this point that there is no friction. The work done by friction is zero. So gravitational potential energy is equal to mgh. The energy due to elasticity is 1/2 kx squared, and the kinetic energy is 1/2 mv squared. So we're going to look at some examples of using the law of conservation of energy. The first and simplest example is if we drop in the sled from a height of 72 meters, how fast will it be going when it gets to point A at the bottom here, and then later on point B? So we're going to let the total energy at the top, which is mgh, equals the total energy at the bottom, which is 1/2 mv squared. So if we do that, total energy at the top, when the object is over here at the top, it has energy equal to mgh. When it gets down to the bottom, point A, all that energy is changed into kinetic energy. Notice that the masses cancel, so the velocity will be independent of mass. So solving this for V, we get that the total energy, the velocity at the bottom is 37.6 meters per second. Let us now calculate also the velocity we would have at point B. Point B is right here. So when the sled gets to this point right on top here, how much velocity does it have? What is its velocity? Again, we're going to set the total energy at the top, which we already did, mgh, h being 72, equals total energy at point B. Now, at point B, it has two types of energy. It has height of 40 meters, given here, and it also has kinetic energy as it's moving along here. This is a picture of what is happening. So the object starts at the top, has gravitational potential energy. All that energy is changed into kinetic energy at point A at the bottom. And when it gets to point B, it has both kinetic and potential energy. So at point B, energy at the top is just mgh, just like before. But at point B, the energy is 1/2 mv squared plus mg times that lower height, mg4h. And once again, all the m's cancel off here. And our mission, of course, is to find the velocity. In other words, solve this equation for v. And so that's what we do in the next two steps, and v is equal to 25 meters per second. Let us add a spring now to the situation. In this case, a toy sled is compressed 0.2 meters against a spring whose spring constant is 500 newtons per meter, and released. And the question is, how high does it go? Once again, let's call this point A, and let's call this point B when it gets up here. Total energy at point A is equal to total energy at point B. So stop the video and see if you can do the problem and find the correct choice. Now the total energy at point A is just 1/2 kx squared. That's the total energy it has when you hold it here, and then just as you let it go, it has that energy plus I forgot here, it has height. This is the total energy at point A. 1/2 kx squared due to the spring being compressed here, and mgh, this is h, due to the height. At point B, it only has one type of energy, mg times, that's capital H. That's a different height than the first height. And our mission, of course, is to find what that capital H is. So basically, if you place in all the values for K, 500, for X, 0.2, squared, that's 1/2 kx squared, plus mg, this is 1, that's called G10, times the initial height, which is 2, equals to 1 times 10 times h. So at this point, it's pretty simple algebra. All you have to do is calculate what, and you can check yourself that h turns out to be 3 meters. So it'll go 3 meters high. Okay, let's do another calculation with friction now. Supposing you start from a high mountain, 52 meters high, and go down, ski down a mountain, assuming there's no friction on the mountain, but when you get on the flat part, there is friction. And the coefficient of friction is 0.2. And the question is, what's the stopping distance here? Given that this is how much energy you have at the top, and that when you get here, friction stops you, the work done by friction stops you, what's the stopping distance? Well, again, we're going to, the total energy that you have at the top is going to equal the work done by the force of friction, because you will have no other energy at the bottom except that energy, or the energy that was lost to friction. So all the energy at the top equals the energy at the bottom plus the work done by friction. But the energy at the bottom, once you get to the very end here, down to the end, is zero. This is just zero. So all the energy you had in the beginning, which is mgh, went to the work done by friction. Of course, the work done by friction is equal to mu times the normal force, which is mg in this case, times the stopping distance, which is what you're looking for. You notice that the masses cancel here, the g's cancel here, and therefore mu is just equal to h, the initial height you had, d, which is what we're looking for in this case, is equal to h, which is the initial height you had, divided by mu. So the initial height you had was 52. Mu was 0.2. which is equal to 260 newtons, 260 meters. So the correct answer is here. A similar problem is, let's say we compress a spring and just shoot this thing up. How high does it go? If the spring constant is 20, if we compress it by 10 centimeters, and the mass of the cart is 50 grams. So basically all the energy right here, which is 1/2 kx squared, that's all the energy it has. All the energy at the bottom at this point equals all the energy at the top at this point. Well, at the top it's just mgh. And so using the numbers you have here, 1/2 times k. Now here's something very important. The units have to be consistent. It should be in meters. So 10 centimeters is 0.1 meters. And you have to square that. Similarly, mass must be in kilograms. So 50 grams is equal to 0.05 kilograms times g, let's use 9.8 here, times h. Now you solve this equation for h, you should get approximately 0.2 meters or 20 centimeters.